Okay, so in the last class we discussed that first we discussed how to get the probability density of the end-to-end distance of a chain. First we did for a one-dimensional random walk, and then we generalized the idea for a three-dimensional general random walk, and finally we discussed that we can relate the probability density with the elastic energy of the polymer chain. Okay, so I want to continue on that discussion and talk about some other models of polymer chains, and then finally we will look at briefly how can we do the same things that we have derived by equations by some kind of simulations. So just to recall what we said, that the elastic energy of the polymer chain is given as 3/2 kBT Re square by mb square, and this has entropic origin. Now this particular result has a very special significance. So if you think of like a metal and you heat it, you normally see the metal expands on heating. On the other hand, if you take a piece of rubber and you heat it, what we do see is rubber shrinks on heating. Okay, and this can be explained by the very idea that the elasticity in the case of a polymer, rubber is of course a cross-linked polymer, has an entropic origin. So when we heat it, as we know, as we raise temperature, the entropy of the system increases and it wants to go to a higher entropy state, and the higher entropy correspond to the case when we have more conformations. So raising temperature, we want to go to higher entropy, and that means it wants to go to more number of conformations, and you can think about this, the more number of conformations will correspond to the case when the value of Re is small. Okay, so think of an extreme case, think of like a chain is completely stretched, then in that case there is only one conformation of a chain when the end-to-end distance is same as the contour length. But if I think of say Re is equal to Lc/2, then that can be achieved in many conformations. This also have the same Lc/2, this also have the same Lc/2. So if I start thinking of lower values of Re, we can think of more chain conformations. That means we are going to higher entropy. This we have also got from the probability density curve that we derived. Actually for Re equal to 0, you have the highest number of conformation because these are the ones which are most probable. The probability actually decreases as I go to higher values of Re, either way in the positive side or negative side. Okay, so that is one important result that comes from the entropic origin of elasticity. The other thing that we said is I can associate the polymer chain model with some kind of spring model with a spring constant that is given by 3 kBT by mb square, kb being the Boltzmann constant and T being the temperature in the Kelvin, and which has a length equal to Re. Okay. So there are a couple of problems with this model. This works beautifully in many cases, but there are some problems. One of the main problems is in this particular case we do not really limit the maximum stretching of the chain. The chain can really stretch indefinitely. Okay, and if you think about it, there has to be a maximum limit which is given by Re is equal to Lc when the end-to-end distance is equal to contour length. That is not prevented in the model we discussed. In our case, what we do have is, if I look at the elastic energy, it does increase as the RE increase, but nowhere do we say that there has to be a physical limit on how far the RE can go. Okay. So, it turns out that this particular approximation, it is also known as the Gaussian chain approximation or the ideal chain approximation, only works for small deformations of chain. If the RE is really very high, then in that case we have to have improved models that somehow capture the fact that there is a maximum value of RE that is given by the contour length. So, those models for smaller values of RE will behave something like a Gaussian chain, but then it must become very steep near the point when RE approaches LC on the either side. It must become very steep at this point. That means that for RE higher than LC, E elastic should really go to infinity in improved models, and in this case E elastic does not tend to infinity. Okay. So, one of the models is known as the inverse Langevin model, and you can read about it. We will not discuss in the class, but this is one thing we have to keep in mind, that the approximation we have derived only works for small extensions. If the chain extension is, say, more than, say, 50% of the contour length, in that case we should be thinking of some other improved model. This is, by the way, I would say a standard model in many of the cases of in physics as well. This is also called an harmonic approximation that only works for small deformations around the mean value. Okay. So, this is one important point. The other point is, we can also associate, just like we can think of an energy, we can also think of a force that we require to hold back a chain at a particular value of RE. Just like if I want to stretch a spring, I have to apply certain force to get it to certain length. In the same way, if I want to maintain a certain value of RE, I do have to apply certain force to it. Okay? And the force is given by the derivative of the energy, because we know, if I have to look at the energy, energy is given by the force multiplied by the displacement, the integral of that. In the same way, the force to hold the polymer at a particular value of RE will be given by the derivative of the elastic energy that we have derived. And in general, we are looking at the vector RE. Okay. So, since we have derived that E elastic is 3/2 kBT RE square by MB square, to take the derivative with the vector RE, what we can do is, we can of course take the constants out and replace RE square with RE dotted with RE, and then what we have is basically from here we can get 2 multiplied by RE, which is 3 by 2 and 2 will cancel out. So, we have 3 kBt by mb square Re, and that force of course has a direction. That force has the same direction as the end to end distance vector Re. So, in the same direction we have our force acting to hold the chain in its position. Okay. So, now this is like where we have come starting from the random walk models, and what we have seen here is we are replacing the polymer chain with one spring of a certain stiffness constant. Okay. So, now we can extend this idea to a bit further by noting that if I cut this polymer chain into pieces, we still have polymer chains. So, we can think of those cuts also as effectively a Gaussian chain. So, what I mean to say is, if I have a polymer chain like this, and if I say cut the chain at, as for example here, and then for example there, then for example there, and so on. Now, these individual cuts also represent a polymer chain, right, because since the m is very large, any particular if I do like m by 2 or m by 3, that is also very large, right. So, we can start thinking of not really a single spring, but many of these springs that my polymer chain is composed of. Okay. And the advantage of doing this is, unlike the first case where I represent the polymer chain by simply one spring, we now have some sort of internal flexibility inside the polymer chain. So, if I now replace this guy with something like this, what I have is actually a collection of springs. Each of them will have a spring constant k, but each of them will have different extensions. Okay. And I can refer to these guys now as some sort of bead, and I can refer to these guys now as some sort of springs, and the model we thus form is known as the Bead-Spring Model, which become especially useful if I am trying to simulate the behavior of a polymer chain. That is one use of it. The other use of it is when I try to look at the dynamics of a polymer chain. If I used the earlier model, there is no internal flexibility being considered. It does capture the mean square end to end distance correctly, but it does not tell me like what is the internal structure of the polymer chain. And if I go for this detailed model, I can also account for the internal flexibility. Okay. But the idea simply extends from the model we discussed. So, we will not completely derive this model, we simply state the relationships for this particular model. So, I can say that these beads have positions R0, R1, R2 and so on, and so for any spring in the system, let us say I look at the nth spring, that is between R n minus 1 and R n, this spring will correspond to certain energy U n, as like this. So, now I have replaced the mb square by b square again. So, these springs become like my segments of the polymer chain, and then each of the springs has this particular elastic energy. Okay. So, if I look at the probability distribution of this particular bead-spring model, so now we do not look at just the end-to-end distance of the entire chain. I can look at the end-to-end distance of the individual springs, or in general I can look at the positions of all the beads, which I can write in shortcut notation like this. What essentially it means is basically all the positions R0, R1 to Rm, and this will then be a product of the individual probability densities for each of the spring. Okay. So, for each of the spring now is a Gaussian spring. For each spring we can associate a probability density, and so at any given moment the probability density for the entire chain will be a product of the probability densities of the individual segments. Okay. And this model becomes particularly useful in simulations, as we will discuss later. So, now I want to briefly touch upon how can we simulate these polymer models, not specifically the bead-spring model that we come to later, but the other models that we have discussed earlier, and see like there is an alternate way to get the results that we have derived, and the alternate way also promises to be more versatile in the sense that we can make those models more complicated than what we can analytically derive. Okay. So, let us say for example, we consider the simulation of freely jointed chain. So, now earlier we did the analytical derivation to get the mean square end-to-end distance Re square. So, now the idea would be that the ensemble average that I am getting here we will now get by simulations. So, essentially what we have to do, we have to simulate many chain conformations, compute their Re squared and take the average of all of that. So, provided that we are generating a very large number of conformations, we can hope that the simulations will give me the same results. Of course, for a smaller number of conformations this may not be accurate, because the idea of the thermodynamics is that the ensemble size must be very large. So, but we can do that in typical simulations. So, the model we are after is this freely jointed chain, and we can generate this in the following way. So, we can start from say origin. So, let us say in the first step we start from origin 0 0 0, which becomes my first point, that is right here, or we can call it R0, and the subsequent point I will generate at a distance b from this R0. Generate next point and there is a particular way of doing it. So, let us say if I have started from this point, if this is my r I, then r I plus 1 has to be at a distance b, but then it can be in any direction in the 3 dimensions. So, the way to think about it is we will draw a sphere of radius b around r I, and then I will choose any point on sphere surface as r I plus 1, where the sphere has a radius p. So, we can use the idea of spherical coordinates, and by that what it amounts to is we can choose randomly the spherical angles theta and phi, where theta has to be between 0 to 2 pi and phi has to be between 0 and pi, and the position of the next point then becomes x I plus b cos theta cos phi, the y coordinate become y I plus b cos theta sin phi, and z coordinate become b sin theta. Okay. So, provided that we are generating points randomly on the sphere surface, that is at radius b with respect to r I can get the new coordinates, and then I can repeat until required number of points, which for m segment case would be m plus 1 are generated. Okay. And then we have to repeat for large number of conformations, and for example evaluate R E square and then take the ensemble average, and then we have the result. Okay. So, this is the way of doing it. There is only a small problem here, that if I use this particular method of generating my random point on the sphere surface, it turns out to be inefficient, in the sense that it will not generate points uniformly over the entire surface. You will tend to have more points near the poles and lesser points near the equator. An alternative way is to generate two random variables, u between 0 and 1 and v between 0 and 1, and then generate theta as 2 pi multiplied by u and phi as cos inverse 2v minus 1. As an assignment, you can try doing both these methods and see why I am saying that you will not get a uniform distribution in this case, and why this will ensure uniform distribution. Okay. So, once we have got this idea for a freely jointed chain, so we can of course get the ensemble average of R E square. We can look at the probability density distribution of conformations. We simply look at what is the probability of having conformations within a range of R E values and so on, and we can reconstruct the probability density curve, the mean square, ensemble average, and all the quantities we have simply derived. And actually we can also see how the structure of polymer chain is changing for different conformations. So the same idea we can apply for other models, particularly the one-dimensional random walk is extremely simple. So I want to do a walk of m steps like that, where I can move left or right with equal probability. And the way to do that, again I can start from origin, then you generate next conformation to left or right with equal probability, that is 1 by 2. And the way of doing it is you generate a random number say between 0 and 1, and let us say I call this number r. If r is higher than say 0.5, we move to the right, that is we do xi plus 1 is equal to xi plus b, and if else if r is less than 0.5, we move to the left with xi plus 1 as xi minus v, and then we repeat for m steps, and then repeat for large number of conformations. If I am doing, for example, a random walk in 2 dimension or higher dimensions, all that changes is my algorithm here. So if I am doing, for example, a 2D walk, so now we have 4 outcomes, left, right, up and down. So now we can again generate r between 0 and 1, provided that it is uniformly distributed from 0 to 1, and now we can say r less than 0.25 move left, for instance. So xi plus 1 becomes xi minus b, yi plus 1 remains unchanged. If r is between 0.25 to 0.5, we do move right. The reason why I am doing this is it is equally probable for r to be between 0 to 0.25 and 0.25 to 0.5. This will happen with a probability of 1 by 4, and in that case we do xi plus 1 is equal to xi plus b, and yi plus 1 is equal to yi. Then again for r between 0.5 and 0.75, we can move up, and then we have xi plus 1 unchanged and yi plus 1 is equal to yi plus b, and then between 0.75 to to 1, we can move down, and now xi plus 1 is equal to xi and yi plus 1 is equal to yi minus b. There is a small detail here that of course r can take a value of 0.5 in this case. That will not really make much difference here, but it has to be r greater than equal to here. Similarly, we can put greater than equal to sign at these intervals, depending on also your generator for the random number, but that will not really make much difference because r is a floating variable that is changing in a continuous way from 0 to 1. Okay. So, the same idea we can also apply if for the 2D walk, if I am not allowing for the folding back, the only difference would be is so I do not want to allow for this possibility, right. So, this is my positions Ri plus 1, Ri plus 2. So, I have to make sure that Ri plus 2 is not equal to Ri. So, we add a constraint in the algorithm that we had earlier. We can generate in the same way, but now with a constraint that we will not allow xi plus 2 is equal to xi and so this is like the AND operator. So, only when both of these are true we should disallow it. Both should not be true. Of course, xi plus 2 can be equal to xi, but yi plus 2 can be different, and that will not amount to a folding back. Okay. So, this is a way we can simulate the variety of models that we have discussed. Keep in mind that in all these cases we are simply enumerating conformations. There is no energy coming into this picture. We simply enumerate many possible conformations and we take an ensemble average. We do not say that these conformations have higher energy and these have a lower energy, and so it turns out that we have to generate many conformations irrespective of the actual scenario where some conformations can be much less probable and they can be avoided. Okay. So, the smarter algorithms that we will discuss in the class later try to incorporate this energy into the picture, and we will discuss in particular what is known as the Monte Carlo algorithm and what is known as the molecular dynamics algorithm, which also require energy calculations. Okay. So, more on that later, but right now what we have done is actually some sort of a Monte Carlo, if you can think about it, but basically we are simply enumerating all possible conformations and then try to see like what conformations are more probable by simply this enumeration process. So, you can write this kind of codes in any language of your choice and try to visualize how the polymer chains look like. That should give you the feeling of what we have covered in the class so far, that why are we saying that there are more conformations for lower values of Re. This we should see by doing this kind of simulations. We can also establish the scaling laws Re square proportional to m, and you would see that this would hold for large values of m. This also we can establish from these kind of small simulations. And finally, once we are in the habit of doing this, the same scheme will go into a more detailed Monte Carlo code, except that we will also have an energy calculation embedded into it. So I want to stop with this. Thank you.